So today we are going to be talking about piezo-resistive sensing. All right. And so before we talk about schemes and the applications of piezo-resistive sensing, we probably first need to understand what the piezo-resistive effect is. So the piezo-resistive effect, put simply, describes how the resistance of an object changes when the object undergoes mechanical deformation or stress. So if we consider a simple beam structure, not going to get wild in the details here since we've already covered most of these relationships. So if we have a simple beam structure like so, that has some length L and some cross-sectional area A, if we subject it to a stress or strain, we are going to see that the dimensions of our object change. A bit exaggerated, but it'll be okay. And then here is our strain in what I'm calling the x direction, right? So the resistance of our original object, R, is a function of both the material properties by the resistivity rho E, the length, and the cross-sectional area. So it's a function of both material properties and geometric properties of our system, right? So it's pretty easy to understand why mechanical deformation will cause a change in resistance, okay? Now, the obvious reasons are because we're changing the length and we're changing the cross-sectional area, right? So we can define a fractional change in resistance, delta R over R, as a fractional change in length. Sorry, that should be just L in the denominator there. And then because the area is getting smaller, why isn't the stylus working? Delta A over A. But then we're also going to have an additional term here. Change in resistivity over resistivity, okay? So this change in resistivity occurs because the resistivity of a material is dependent on its internal atomic structure. And when we deform a crystalline structure, we're stretching out those atomic bonds slightly and things like that, causing a change in the overall resistivity. So we are going to define a piezoresistive coefficient, pi, as the change in electrical, the fractional change in electrical resistivity per unit stress, or fractional change in resistivity divided by the Young's modulus times our strain, okay? So while this looks like a relatively straightforward equation here, piezoresistivity is an anisotropic property. Actually, I don't remember. Whichever one means it's dependent on directions. I can't remember if that's anisotropic or isotropic. I think isotropic is the same in all dimensions, and anisotropic is changes with direction. What I'm meaning here is that directionality is important, and we're going to talk about this a little bit when I show you what the piezoresistivity tensor looks like. Okay, so another important figure of merit that we are going to use to characterize the piezoresistive effect is what's known as the gauge factor. So our gauge factor, GF, is defined as the fractional change in resistance per unit strain. So that's going to be the change in resistance divided by resistance over strain is change in a lateral dimension over the lateral dimension itself, so delta L over delta L. And if we substitute in this relationship into our previously developed relationships, we'll find that this is going to look like 1 minus the change in area over the area, or the fractional change in area, divided by the strain, plus the fractional change in resistivity divided by the strain, and tying things back together with our review of stress and strain relationships. The change in area over the change in length is governed by Poisson's ratio, so we can reintroduce that here. So we're going to have 1 plus twice Poisson's ratio. The sign changed because Poisson's ratio is usually negative. It's a transverse. And then we're also going to have plus E, our Young's modulus, times pi, our coefficient of piezoresistivity. Okay, so this is what our gauge factor looks like. So the first two terms are the geometric contributions, the gauge factor, and this last term is the material contribution to the gauge factor. Okay, so if we look at the geometric contributions, since Poisson's ratio is usually somewhere in the ballpark of 0 to 0.5, at most, we should expect a gauge factor of about 2 due to purely geometric changes. So if we look at a list of materials here, I'm going to write you guys a little table. Straight enough for my taste. And then over here on the right hand side, we're going to have gauge factor. So aluminum has a gauge factor of 1.4, meaning effectively that any piezo resistive effects are due to geometrical changes predominantly. Copper has a gauge factor of 2.1. So also, we're assuming here that the predominant effect is geometric in nature. Platinum, 2.6. So we're starting to see some material properties creep through. Nickel, negative 12.62. So that simply means that the resistivity goes down when we mechanically deform it, but it is a pretty appreciable change, right? So this is significantly larger in magnitude than 2. So the material properties have a lot to do with this. This is the exact reason that nickel is used for macro mechanical strain gauges. If you were to go to Bogart Hall and look at any of the strain gauges or anything like that, you use, or at least I used to use way back when I took statics and all that kind of jazz, they're all made of nickel. And the reason is because nickel has a very high gauge factor. Well, for micromechanical systems where we use polycrystalline silicon or single crystalline silicon, what we're going to see is that, so for crystalline silicon, our gauge factor is going to range from negative 30 to positive 40. And for single crystal silicon, it'll range from about negative 102 to positive 135. So the reason why those ranges are so large is because our gauge factor is dependent on our piezo resistivity coefficient, which is in turn temperature dependent, dopant dependent, and really the type of dopant. So dopant dependent and dopant concentration dependent, I guess would be another way to put it, right? So it matters if we dope the material N type or P type, that's going to change our piezo resistivity coefficient. The temperature at which we are operating our device changes the piezo resistivity coefficient, so we're going to get a large range of things. The relatively large gauge factors of silicon make it an extremely attractive material for use in piezo resistive devices. So most early MEMS sensors were piezo resistive, and then because of things we're going to talk about in this class, capacitive sensing and things like that were introduced later on. But it's still the technology is still very widely used. Okay. So let's talk now about the piezo resistive properties of silicon. So for crystalline silicon, if the X, Y, and Z axes are aligned with the 100 family of planes, the relationship between resistivity and stress is expressed as follows. So we're going to have delta rho 1 over rho naught here, delta rho 2 over rho naught here, delta rho 3 over rho naught here, delta rho 4 so this is going to be a big ugly matrix. Okay, so these are fractional changes in resistivity that are going to be caused by stresses in different directions. Okay, so now I'm going to give you guys the piezo resistance matrix. So we're going to have pi 1, 1, pi 1, 2, pi 1, 2, 0, 0, and 0, pi 1, 2, pi 1, 1, pi 1, 2, 0, 0, and 0, pi 1, 2, pi 1, 2, pi 1, 1, 0, 0, and 0, 0, 0, 0, pi 4, 4, 0, 0, 0, 0, 0, 0, pi 4, 4, 0, and 0, 0, 0, 0, 0, pi 4, 4, multiplied by our different stresses. So this first element in this array is going to be stress in the x direction, then stress in the y direction, then stress in the z direction. So here we have our normal stresses. And then here we're going to have TYZ, TXZ, and TXY, or our shear stresses. Okay. All right, so from this relationship, we can see that there are really only 3 independent piezo-resistant coefficients that are telling us how this thing is going to behave. Pi 1, 1, pi 1, 2, and pi 4, 4. These constants, or these coefficients, actually, let me put it that way. These coefficients, pi 1, 1, pi 1, 2, and pi 4, 4, are not constant, but are influenced by dopant concentration, dopant type, and temperature. So for dopant concentrations Na and Nd less than 10 to the 17 per cubic centimeter at T is equal to 300 K, what we will have are, so this is going to be another table, so bear with me here for a moment. Here is our piezo-resistive coefficients having units of 10 to the negative 11 inverse pascals. And then here is what we will see in N-type crystals. And over here is what we will see in P-type crystals. Pi 1, 1 will have a value of negative 102.2. And for P-type crystals, it'll have a value of positive 6.6. Pi 1, 2 will have a value of approximately 53.4. For P-type, it'll be negative 1.1. And for pi 4, 4, we're going to have negative 13.6 and positive 138.1, respectively. So these are telling us the direction dependent properties. And so we're going to do one last thing here with all these terrible tables. We are going to summarize what the overall piezo-resistive coefficient is going to look like for different directions of strain and different directions of current passing through part of this, right? So last table that I'll make you guys suffer through. Do I need to go back? 1. All right. So if our strain is in the 100 family and our current, sorry, is in the 100. So effectively, if our strain and our current are parallel to each other, we have a longitudinal configuration. And our piezo-resistive coefficient is simply pi11. If our strain, I'm writing this wrong, is in the 100 direction, and our current is in the 010 direction. So what I mean by that is effectively our strain and our current are 90 degrees displaced. We have a transverse configuration. And our piezo-resistive coefficient is simply going to be pi12. For strain in the 110 direction and current parallel to that, we'll once again have a longitudinal configuration. And the overall piezo-resistive coefficient is going to be a combination of our direction-dependent piezo-resistive coefficients. So it's going to look like 1/2 pi11 plus pi12 plus pi44. And for a transverse configuration for 110 strain, we're going to have something similar, except that the pi44 term is going to have a negative sign associated with it. And then lastly, for 111 strain direction and current direction, we're going to have 1/2 pi11 plus twice pi12 plus twice pi44. So the reference that I got this information from, effectively this matches very well with the official textbook for this class, but I think does a little bit better job of explaining where things are coming from. It does not have any information for a transverse configuration for the 111 crystal plane. And quite honestly, I didn't have time to go look through papers and see if I could figure that out. So I'm just not going to deal with it for now. That'll be a thing to do for later. All right. So circling back around, our gauge factor can be determined by multiplying the piezo-resistive coefficient with Young's modulus. That Y should be capitalized, my apologies. In the direction of applied strain. our gauge factor will be approximately equal to pi times the appropriate Young's modulus, right? Such that the total fractional change in resistance is given by delta R over R will be the fractional change in resistance due to longitudinal effects plus the fractional change in resistance due to transverse effects. And we can do a little bit of manipulation here. So this is going to look like our longitudinal gauge factor times our longitudinal strain plus our transverse gauge factor multiplied by our transverse strain, and putting the relationship that pi e is our gauge factor and ES is our stress. We finally come up with a fractional change in resistance expressed only in terms of piezoresistive coefficient and applied stress. So that's going to be pi longitudinal times T longitudinal plus pi transverse times T transverse. All right, so it is often the case that only one of these components are dominant. Seems pretty reasonable. So let's work an example problem. How much space do I have? That's like enough. So let's say that I have the following microstructure, okay? So over here on the left-hand side is effectively going to be my anchor. I'm going to have a long cantilever beam. And this beam will have a length of 200 microns. Attached to the end of this beam, oh sorry, while we're at it, the width of the beam will be 20 microns, and I'll just put it out over here. Beam thickness T will be equal to 5 microns. All right, so attached to the end of the beam, I'm going to have a proof mass. Where the dimensions of my proof mass are 50 microns by 50 microns. And I'm going to say that there is a point force directed into the page F, going to cause my cantilever beam to deflect into the page. Where my applied force is 25 micronewtons. And integrated onto this cantilever beam proof mass structure will be piezo resistors, okay? So I'm going to do these just in a slightly different color here. So I'm going to have two piezo resistors in series. Connected like so. This is going to be the 110 direction of our crystal. And so we're going to have effectively longitudinal strain. The dimensions of my piezo resistor. I'm going to have a length of 20 microns, a width of 5 microns, a thickness of 0.5 micron, and my resistivity is going to be 11.7 ohms per centimeter. And I want to determine two things. Number one, what is the fractional change in resistance experienced by one of the piezo resistors? Since there are two in series, if we wanted the combined effect, we would just multiply it by a factor of 2. Due to the .25 micronewton force. And number 2, what is the absolute change in resistance? And then the rest of the sentence is the same. So before we get into the math here, let's talk about a couple of things. For this cantilever bending, why am I choosing to integrate our piezo resistors at the location that I have chosen? Does anybody have any thoughts? Exactly right. So the maximum stress and the maximum strain for a cantilever beam occurs at the location of the anchor point on the surface of the beam. So if I want to get the maximum change in resistance due to the piezo resistive effect, I need to integrate my piezo resistive sensors at the anchor point on the surface of the beam. Now I could integrate them on top of the beam using a deposition process, or I could integrate them literally into the beam using a doping process, right? Selective doping. If my structure is made of single crystal silicon, I can just do ion implantation and make a piezo resistor effectively inside my beam using light doping, and then I can pattern my wires that are connecting things using heavy doping effectively. And because piezo resistivity is dependent on dopant concentration, what we actually find out is that when you have a region that's heavily doped, its piezo resistive coefficient is significantly smaller. So that means our fractional change in resistance of our wires is going to be less pronounced than the fractional change in resistance of our purposeful piezo resistors. So things work out in our benefit in that sense, okay? The dimensions of the piezoresistor are actually critically important as well, and we're going to talk about that in a little bit in more detail. But a couple of things that it is important to note here is that the thickness of the piezoresistor needs to be appreciably smaller than half of the thickness of the beam itself. Anybody have any thoughts on why that might be important? So for cantilever bending, everything above the neutral axis is under tensile stress, and everything below the neutral axis is under compressive stress. So if the thickness of our piezoresistor goes beyond the neutral axis, some of those stresses are going to wind up canceling each other out. So that portion of the piezoresistor doesn't actually do anything. We have decreased sensitivity and increased processing costs by integrating the device that deep into the device. So generally speaking, we want it to be thin in comparison to the thickness of the beam. That being said, the resistance of the device depends on that thickness due to its cross-sectional area and all that kind of stuff. And so as the resistance goes up, since this is a piezoresistor, it is inherently a thermal noise generator. So the larger the resistance that we implement, the larger the noise our device generates. So there are trade-offs there as well, okay? So we've talked about the importance of the thickness of our piezoresistor. What about the length, right? Anybody have any thoughts regarding the length? Why that might be important? Is this stress/strain that the cantilever beam undergoes constant? No, its maximum value is at the anchor point, and at the free end of the cantilever beam, it's effectively 0. So we want to make our piezoresistors short in comparison with the length of the cantilever beam itself, so that we can say with a reasonable degree of accuracy that effectively the piezoresistor experiences the same stress throughout its length. That won't actually be true, not even close to it, but it's going to give us a reasonable approximation. Whereas if we made these piezoresistors the entire length of the beam, we know for sure that's not true, and we're having a very, very poor approximation, okay? So in general, we want the thickness of our piezoresistors to be smaller than half of the thickness of the beam, and we want the length of our piezoresistors to be small in comparison to the length of our cantilever beam, or the length of our membranes and things like that when we get into pressure sensors and all that kind of good stuff. So where we locate these and how we integrate these is critically important, okay? All right, so now let's do some math. So is our cantilever beam going to be experiencing longitudinal stress or transverse stress? Longitudinal, right? If there's any transverse effects, which we really shouldn't see because we're not trying to stretch the beam, they would be very small in comparison. So we're going to throw all of our transverse bits away. We shouldn't have to worry about those at all. In fact, I don't think they should exist because we're doing cantilever bending. But anyway, so we are going to have some maximum stress. Go back to your notes, or if you want, I'll just tell you, but we have covered what the maximum stress experienced by cantilever beam bending is. So we should be able to go back and literally pull directly from stuff that we've talked about before, how to figure out that portion of our fractional change in resistance. You got something? Force, but not displacement, because I'm too lazy to figure out what the displacement is. So F L and then B, which is the dimension in the thickness direction. So I'm going to write T divided by twice moment of inertia I. Okay. Now, when we derived this, the force was applied directly to the end of the beam, if I am not mistaken. In this case, our length, capital L here, is the length from the anchor point to where our force is applied, which is going to be the length of the beam plus half of the length of the mass, right? So we're going to have F times L beam plus 1/2 of L mass times the thickness of the beam divided by 2 times the modulus, which is based on AB squared, where A is the width dimension and B is the dimension, well, really B is the dimension beam bending and A is the other dimension of the cross-sectional area, right? So we're gonna have the width of the beam times the thickness of the beam quantity cubed. And if we substitute in, and that by itself is divided by a factor of 12. Sorry, I almost missed that. So if we substitute in the numbers from our problem statement here, our maximum stress, which occurs at the anchor point on the surface of the beam, is going to be 67.5 megapascals. So this is just direct application of what we talked about, I don't know, a couple of weeks back. Well, definitely a couple of weeks back after the break and all that kind of stuff, when we were talking about our review of necessary mechanical properties and all that jazz. All right, so now we need to figure out what our longitudinal piezoresistive coefficient is going to be. Okay. So, because we are dealing with the 110 plane, so that's the direction that our stress is applied in, and it's the direction that our current is effectively flowing in, we are going to have 1/2 pi 11 plus pi 12 plus pi 44. And it would be important for me to tell you whether or not this is an N-type piezoresistor or a P-type piezoresistor. So let me go ahead and do that because I just realized I forgot to. This is N-type, so that we know which values from the table to pull. And from here, we could simply calculate our longitudinal piezoresistive coefficient, which is going to come out to be negative 31.2 times 10 to the negative 11 inverse pascals. Putting these two pieces of information together, our fractional change in resistance, delta R over R, going to be pi L times T max is negative 2.106%. So that 25 micronewton force causes roughly a 2% change in the resistance of each of the piezo resistors, right? It should be the same for the overall piezo resistance anyway, though, since they're just both in series. All right, so what about our absolute change in resistance? Well, that's simply delta R. So that's going to be pi L T max times rho E LR over WR/TR. So the length of our piezo resistor divided by the cross-sectional area of our piezo resistor. And in this case, numerically, this comes out to be about negative 19.712 kilo ohms. So inferring from this, our designed resistor is somewhere in the ballpark of a 1 mega ohm resistor, based on its dimensions and the given electrical resistivity. All right, so anything particularly crazy there? Not a problem. All right. Right, so the change in the resistance, like the absolute change in resistance for the series combination would be twice 19.712 kilo ohms, but the fractional change should be the same, right? All right, so I'm going to go into very slightly more detail regarding the placement of piezo resistive sensors. And we're going to talk about two cases of quote unquote good design and two cases of quote unquote bad design. So I feel pretty strongly that we all understand we want to place these in the location of the maximum stress. Okay, so that part's pretty self-explanatory, because the piezo-resistive effect is effectively defined as the change in resistivity due to applied stress. We get the largest result if we have the maximum stress. Okay. With regards to integration though, so let's look at a couple of simplistic renderings here of cantilever beams, right? So let's say that I have cantilever beam like so. And this guy right here would be a doped piezo resistor, or I'm just going to simplify it by calling it R because I don't want to write it out over and over again. And this guy over here would be an example of a deposited piezo resistor. So these are our two examples of effectively what we're going to consider good design choices, right? Where, for the reasons that we discussed previously, we are considering these good because they are thin with respect to the thickness of the beam and short with respect to the length of the beam, such that we're not having any cancellation of force, so we're not losing any cancellation of stresses, so we're not losing any sensitivity. And we can say roughly that our device undergoes a similar amount of stress across its entire length. All right, or similar amount of strain across its entire length. Well, it matters. One other thing that maybe isn't super obvious, but particularly in the case of having a deposited resistor where it's not integrated into the beam itself, our cross-sectional area, we put something on top of the beam, the cross-sectional area that's undergoing deformation and all that kind of stuff technically changes, right? So if that area that we're introducing is small in comparison to the beam's area, it means we really don't have to go through the trouble of recalculating the moment of inertia, changing where our neutral axis is for the system and all that kind of good stuff. So we can get a reasonable approximation even for a deposited structure or a deposited piezo resistor by ensuring that its thickness is relatively small as compared to the beam's thickness. Now we're gonna, sorry.
Is there a reason to do one over the other than just process?
No, I mean, it is literally just cost of processing. So it's a question of, are you going to dope single crystalline silicon to make your piezo resistor, wires, etc., or are you going to deposit polycrystalline silicon to make your piezo resistors, wires, etc.? And then because you are aware of, because you took the integrated circuits class, the polycrystalline silicon is going to have to be doped in order to make it electrically conductive anyway. So it's the cost of processing is going to define that. So bad designs would look something like this. So we're going to have our exact same beams, but for our doped case, the thickness of our piezo resistor has crossed the neutral axis, which once again means that some portion of the piezo resistor is under tensile stress, some portion of the piezo resistor is under compressive stress, and we have canceling out of those effects, which means our device overall has decreased sensitivity. And effectively, we've wasted money and or time by creating such an abomination. Okay. And then for our deposited piezo resistor, if we make it too thick, we can obviously see that the cross-sectional area of our structure has significantly changed, which means we have to reevaluate effectively all of the math that went into the determination of our stress and things like that. Also, we have to take into account the fact that the two different materials may have different Young's moduluses and things like that that are going to come into play in determining any stresses that come into play, or strains, sorry, come into play. So generally speaking, like I said, we want it to be thin in comparison to the thickness of the beam and short in comparison to the length of the beam. Does the width matter? So what is the width of the piezo resistor? What is that going to change? Just speaking strictly about the piezo resistor. Well, if we're assuming that these are all longitudinally oriented, and so the current is flowing in the same direction as the length of the beam. The width is just going to make the area, the cross-sectional area, larger, which will in turn make the overall resistance smaller. It's not going to change the fractional bit at all. Actually, that's not true. If we look at our equation up here. No, the width of the piezo resistor, sorry, yeah, the width of the piezo resistor isn't going to change the fractional change in resistance. It's not going to change the fractional change in resistance at all. It will obviously change the absolute change in resistance because the unstressed resistance of our device will be smaller, right? Which is probably actually a good thing because the larger the resistor we have, the more thermal noise it generates. So anyway, just.
The first formula of del R by R, we have delta L by L minus delta A by A.
Right.
Here we have the area of the
Right, but so if we are dealing with longitudinal stress, should the area change? If effectively, if our cantilever beam isn't undergoing extension, we shouldn't see that the area matters. Now, if we were dealing with an extension rod thing, that could be a different bag of cats. And that's also an interesting thing. So with an extension rod, the stress is uniform across the entire cross section, right? So the location of our sensor doesn't particularly matter. You can argue that it might be best to make it the entire thickness of the beam, and its location along the length of the beam is completely and utterly irrelevant. But under the cantilever examples that we're looking at, the width isn't going to do anything but actually potentially improve the noise performance of the system. Okay. So last thing that I want to talk about for today is temperature dependence. Go back because I wrote my notes in a weird order. So temperature sensitivity of piezo resistance. All right. So I talked earlier about how the piezo resistivity coefficients pi11, pi12, and pi44 were dependent on dopant concentration, dopant type, and temperature. Okay. If the doping concentration is less than 10 to the 17 dopants per cubic centimeter, which is effectively the threshold we're going to use in this class because that's the only thing that I have data on. The piezo resistive coefficients tend to decrease with temperature, such that our piezo resistive coefficient as a function of temperature is the piezo resistive coefficient at 300 Kelvin multiplied by the ratio of 300 Kelvin divided by the temperature. In truth, this is only true for small changes in temperature, okay? But for what we're going to be dealing with, that'll be fine. So effectively, what we should see is that as temperature increases, our piezo resistive coefficient decreases. As temperature decreases, our piezo resistive coefficient increases. And it's inverse of a linear relationship here. Okay. Now, what about resistivity? The material property that determines the resistance of our piezo resistors. What is it dependent on? For you guys that suffered through my integrated circuits class last quarter, you ought to have some idea. It was dependent on carrier mobility. It was dependent on temperature, and it was dependent on dopant concentration. Okay, so for small changes in temperature, we can define a first order temperature coefficient of resistance. I'm going to put TCR1 because we're throwing away multiple parts things here. That's going to be effectively somewhere in the ballpark of 0.15 per Kelvin. So what that means is the resistance will increase about 1.5% if the temperature of the resistor increases 1 degree Kelvin, or the temperature, excuse me, the resistance will decrease by 1.5% if the temperature decreases by 1 degree Kelvin. Okay, so this is change in resistance due to change in temperature measured in Kelvin. So the problem that we have here is that quite often the resistivity dependence on temperature is stronger than the piezo resistivity dependence on temperature, or the piezo resistivity effect in general. So let's say that we had our piezo resistor from the previous example. We want to know the absolute change in resistance due to .25 micronewton force and a 5 Kelvin temperature increase. Okay, so that's the first thing that we're going to find. And that's going to be fairly straightforward because our longitudinal piezo-resistive coefficient at our new temperature, which I'm going to denote by putting a prime there, is just going to be our old piezo-resistive coefficient or longitudinal coefficient times 300K over 305K. So we should see that it gets slightly smaller. It goes from negative 31.2 to negative 30.689 times 10 to the negative 11 inverse pascals. Behaving exactly like what we would expect. Using this new value, we could calculate our change in resistance due to the piezo-resistive effect, including this temperature dependence, is going to come out to be negative 19.389 kiloohms. So slightly smaller than what we had before, which is exactly what we would expect because our piezo-resistivity coefficient was slightly smaller as well. Okay, so that's our change in resistance due to the piezo-resistive effect with a temperature change. Now let's look at how the value of the resistor changes just due to temperature because the resistivity changed. All right. So resistivity change due to temperature. We are going to have delta R, and I'm going to put this subscript T. So this is purely temperature dependent. We're going to have our temperature coefficient of resistance times our change in temperature times our nominal resistance and this comes out to be 70.2 kilohms. So in crystalline silicon, resistivity's dependence on temperature is about 3.5 times larger, and this is for N-type materials, than the piezo-resistive effect. Which begs the question, if we have an environment where we don't have temperature stability, can we use piezo resistors to measure accelerations, forces, etc.? And the short answer is not by themselves. Okay, we're going to have to include other resistors and do ratiometric sensing. And we're going to talk about that at the beginning of our next period class, or the next class period. But effectively, if we use ratiometric sensing, the temperature dependence cancels out, because if everything increases by the same amount due to temperature, temperature is no longer important, at least to a first order approximation. So we'll go through ratiometric sensing using resistors, and then talk about power consumption, things like that, and then do a little bit of noise analysis, and then we'll be finished up with this, and we'll move along to piezoelectric sensing on Monday's class period. All right, thank you for indulging my rant. I replaced, just for those of you who are interested, this is my old notes from when I taught piezoresistive sensing back when I was a grad student. And I replaced this first 2/3 of a page with 6 pages of notes. Trying to do a little bit better of a job, for better or worse. All right. Thank you guys, and I'll see you on Monday.